Welcome to our lecture series on protection technology. These free Siemens Power Academy lectures are designed for those who want to expand their knowledge and understanding of relay protection for distribution and transmission grids. My name is Jackson da Silva and I'm Senior Trainer from Protection System at Siemens Power Academy. In these lectures, I will have the honor to be the moderator. Today, we will focus on distance protection and parallel lines, mainly for professionals from distribution and transmission grids. We will record the webinar and make the recording and slides available to all participants. Please type your questions in the Q&A field. We will answer these during a dedicated Q&A session after the series. And now, let me hand over to our expert, Prof Lemmer. Siegfried, the stage is yours.
Hello and welcome to this session on distance protection and parallel lines. You may have heard if you apply distance protection on parallel lines, you have to consider some strange effects which happen there. And you may also have recognized in our manuals that we have a chapter about parallel line compensation. So in this video, I will explain what is behind these topics if you apply distance protection on parallel lines. Let's start with some general consideration. What is parallel line? And there are different configurations possible. So I would like to start with this configuration you see here. In this case, we have one line on the bottom, and we are talking about a distance relay protecting this line. And this line has in parallel for a certain distance another line. They are on the first section on the same right of way. Maybe we have they use the same tower. So we have two systems on the tower. And then this line goes into a different direction. In this case, we have a situation where part of the line is a parallel line section. And there you see, and that is indicated here with a dotted line, if you have now a short circuit on the line, the distance relay measures the distance of the short circuit, then part of the short circuit comes along this red dotted way, and you see here in this parallel section, the short circuit goes first in one direction and then on the parallel line in the other direction. And that means both systems on this parallel line have short circuit current and they influence each other. And that generates a measurement error which makes us some trouble in distance protection. So that is a thing we have to consider. Another option is this one. Here you see real parallel lines. So from A to B we have parallel lines. But here in this case both substations are double busbar substations. And here I assume, and that is a situation you will also often find, that the two parallel lines are on both sides not connected to the same busbar. And the effect can be, it depends a bit on the topology of the system, the effect can be that if you have a short circuit on one line, as indicated here on the bottom line, that the current on the other line is not significantly influenced because it belongs from the topology to another part of the system. In such a case, it looks like a parallel line system, but if the situation is like described, if you have no significant part of the short circuit current on the parallel line, you have no influence, you can ignore it. The standard case, or the case where the parallel line influence is biggest, is this one. And that is the situation I will consider in the following slides. That means we have two parallel lines. They are connected on both ends. And then, in case of a short circuit on one line, as indicated, part of the short circuit current comes through our relay, which is indicated there, and another part of the short circuit current comes via the parallel line and then from the other side to the influence to the short circuit, and also a part is coming from the right side. And again here you see the two parallel lines both carry short circuit current and they influence each other, and that is the influence we will now investigate a little bit more. In this slide you see again this arrangement. You see the two parallel lines connected to the same bus bar on both ends, and in this case I indicated all four protection relays. We assume that these protection relays are distance relays. If there were differential relays, we wouldn't have to talk about this issue. On the right side you see a picture of such a line. That's a typical arrangement. Both systems on one tower, so they are pretty close together so that they can influence each other. We will see in the following slides that the influence, the effect we are discussing here, is biggest if we have a weak infeed or even no infeed from the right side. So for the first considerations, I will open the breaker here on the right side as indicated now. It's not a typical situation in transmission systems, but to understand the effect it's best to start with that. If we now have a short circuit on one line as indicated here, part of the short circuit current comes from the left side through our relay, which has to react on the fault, and part of the short circuit current goes via the parallel line and comes from the other side. And the ratio between these two currents depends on where the fault is. If the fault is near the right side, it's nearly 50-50. If the fault is pretty much close to the left side, the big majority of current comes the direct way and only a small portion goes the long way to the other substation and all the way back. And what you also see, and that's again indicated by these blue arrows, as soon as we have short circuit current on the parallel line, there will be some influence. That means a current flow on the parallel line will induce voltage into our line, and this voltage is seen by the relay and it will to a certain extent disturb our measurement. And this induced voltage, which leads to measurement errors, the amount of this voltage of course depends on several parameters. If we have a long section where these lines are in parallel, of course we have more induced voltage. If the section is short, or if the parallel line then goes a different way, it reduces the induced voltage. So it depends on the part. Of course it also depends on the amount of current on the parallel line. If we have a lot of current on the parallel line, we will induce a lot of voltage. If we have no current on the parallel line, we can ignore the effect. And that is a bit the complicated thing, we have to look at the coupling factors. That means how strong is the magnetic coupling between the parallel line and our protected line. And that is a thing which is a bit more complicated. It can be calculated. You may know if we calculate three-phase systems, we normally separate the system into symmetrical components. That means we separate the system into positive sequence, negative sequence, and zero sequence systems. And the point is here, the coupling is mainly effective only in the zero sequence system. That means theoretically we have a coupling in the positive sequence system, in the negative sequence system, and in the zero sequence system. But if we calculate the coupling factors, and they can be calculated by programs taking into account the geometry of the towers and the cross-section of the conductors and so on. If we do that, we see that the negative sequence system is the dominating thing there. And you can understand that if you look at a simple example. You see here the two systems on the tower, and now we assume we have current flow on the left system, and we want to calculate what is now the induced voltage into the right system. And that means we can look at the three conductors. So you see here the first conductor will induce some voltage into the right system. The second conductor will induce some voltage, and also the third conductor, they all will induce some voltage. If we have a load situation, or if we have a three-phase short circuit, or even a two-phase short circuit, the sum of the current in the left system, the sum of the three currents is zero. And if the sum is zero, that means that these three induced voltages nearly compensate each other. Not exactly, because the distances are a bit different, but they compensate each other to a pretty high degree. And if you have transposed lines, the compensation is even better. However, if you have an earth fault somewhere, that means if you have a short circuit current flowing in the left system, that means you have a current flow only in one conductor, then this compensation is not there. Then you have directly the influence from the conductor with the current into the right system. And that is an explanation why the coupling in the positive sequence and negative sequence system is much lower than in the zero sequence system. That means for us it is sufficient to consider the coupling in the zero sequence system. That is for the calculation. And that also means that measurement errors in distance protection resulting from this effect will only occur if we have zero sequence current flowing in the parallel line. And that, of course, is an interesting thing. That means the effect we are talking about in this video is only relevant for earth faults. Unfortunately, you know that earth fault is the majority of faults, so that means we cannot, definitely not completely neglect that thing, because in the majority of faults this effect is there. Again, one remark on the distance. In this picture I show here, we are talking about two systems on the same tower. That is, of course, the case where the coupling is the highest, because they are as close together as possible. Sometimes, if you have more space available in your country, you may have two individual lines on separate towers, but still close together. Then you still have a coupling. Maybe it's a bit lower, but it's still there. If the lines are 5 kilometer or 10 kilometer away from each other with a big distance, theoretically you also have a coupling, but practically, of course, you can forget it. So it's mainly relevant for lines on the same tower or lines on separate tower, but using the same right-of-way. So now let's look at this effect a little bit more in detail. Unfortunately, I have to show a few equations for that. We look again at this case that our relay, the left bottom relay, wants to measure the impedance from its location to the fault. And here we are talking about earth faults, and that means the relay measures the earth loop, phase to ground loop from the relay through the phase up to the short circuit and back in the ground loop. And you may remember, for that you need this equivalent short circuit I show there, where you have in the upper part the unknown positive sequence impedance of the piece of line from the relay to the fault, and in the ground path you have this sometimes a little bit strange earth impedance, which can be calculated from the zero sequence impedance. That is the equivalent circuit the relay assumes, and to calculate the impedance, it sets up the loop equation in this loop. The result is seen down there, and then you can introduce the earth compensation factor, as I explained that in the basic session, and then you end up at this equation. And it's a bit simplified. Our relays do not exactly work according to this equation, but for the explanation, you can say the relay works somehow according to this equation. The measured voltage that can be measured by the relay is the unknown impedance from the relay to the fault, multiplied by this thing which contains the phase current and the earth current and this compensation factor. And from that simple equation, you can calculate the unknown impedance. If we have this parallel line situation, the real equivalent circuit we should use looks a little bit different. You see here I introduce this transformer that indicates our induced voltage. That means we have basically the same equivalent circuit, but we have this additional transformer which brings us the induced voltage from the current of the parallel line with according to the length of the coupling and also the coupling factors. And that would lead to a different loop equation. That means in the loop equation we get this additional thing there, which consists of a so-called coupling reactance and also the current on the parallel line. That means the higher the current on the parallel lines is, the bigger this effect is, the higher the coupling is, either because the coupling factors are higher or because the parallel line distance is longer, the higher this voltage is. That means this leads to the equation which should be used, but normally our protection relay cannot use this equation because it doesn't know the current on the parallel line. That means we apply this circuit equation on the left side to a system which is shown on the right side, and that causes, of course, a measurement error, and that is proportional to this topic. It's also important to see there, this measurement error can go into both directions depending on the direction of the parallel line current. And now I would like to show you a simulation where we can play a little bit with this situation so that you can see what happens based on these measurements errors. How do these measurement errors influence the distance protection? Yeah, here in this simulation you see the same situation I showed before. You see two parallel lines, and these parallel lines are connected on both sides to the same bus bar, and we have in-feed from both sides. And in this system I can simulate different faults. Here with this slider I can define where the fault is. With these sliders I can influence the short circuit power from the different sides. At the moment you see no current flow. That means there is no load current, no fault, nothing happens. So now we simulate a phase to ground fault. Here, slider says at 50%. This red arrow indicates where the fault is. And you also see that the program now calculates the current. This is a completely symmetrical situation. That means the short circuit power from both sides is the same. The fault is on the middle of the line. That means in this case our parallel line has no current and it doesn't influence the measurement. And what you see here with these green arrows is what these two relays measure. So we have a relay here that measures a distance of 50%, and that relay here also measures a distance of 50%, which is fine because the fault is at 50%. So that's not a very interesting case. So what can we do now? We shift the fault. Of course, that's the thing you can't do in reality, shifting a fault along the line. But here the simulation, we can do it. Now let's shift it maybe to 60%. And what do we see now? The fault is now at 60%. Here, the red thing. And now you already see some measurement errors. You see now the parallel line has current because part of the fault current flows this way. And that means the situation is no longer symmetrical, and that means this current on the parallel line now influences the measurement of this relay and also the measurement of this relay. Here you see the two currents have the same direction, and the result is that our measurement error is positive. That means instead of 60% fault distance, we measure 60 point something, and the right relay should measure, if we have 60% from one side, we have 40% from the other side. It should measure 40%. It measures a little bit less. That means what we see, if the two currents have the same direction, our measurement error is positive. If they have different direction, as indicated here, then the measurement error is negative. Okay, now you can say, complicated discussion, and we are talking about 0.6% measurement error, so that's not a very big thing. But we can look what are the influencing factors, and I told in the beginning one influencing factor is the distribution of currents, and the worst case is you have a very weak infeed on the right side. So let's open the breaker here. I didn't program that in my simulation, but what I can do is I can set the short circuit power here to 0. That means we have no longer infeed from the right side. And now you see the current on the parallel line increases because of our changed short circuit power. There's much more current on the parallel line. And now you see the effect is higher. The fault is at 60% and we measure 68.9%. That means we have now already more than 10% measurement error, and also from this side. An interesting thing to keep that in mind, that is only relevant for face-to-ground faults. So if I change here to a face-to-face fault, everything is fine again. You see, fault is at 60%. This relay measures 60%, the right relay measures 30%. That means this problem only shows up if we have face-to-ground faults. That is the zero sequence story I discussed in the beginning. Now you can say, okay, not nice, 10% measurement error, or more than 10% measurement error. But it's still no wrong protection operation, because the fault should be in the first zone. It is at 60%, we measure 68. Okay, but it's still in the first zone. That means in this case, both relays would react properly, so it's not really an issue. So let's move the fault a little bit more. And now you see what may happen. Now, why is this arrow yellow? In my simulation, I assume that we have a zone setting of 85% of the line. And that is the first calculation where now our relay calculates a fault distance outside the first zone. You see here the result is 86 point something percent. That means now we have the situation the fault is at 72%, but the relay measures the fault at 86 and says, outside the first zone, I will not issue a fast trip. And that is the point where we are getting problems. We expect that the first zone reaches up to 85%, but also at 72% we won't get a fast trip. Then that means we have a significant underreach, 72% instead of 85%. And that, of course, is not nice. Be careful here with the signs. No, I just said we have a positive measurement error. That means we measure an impedance which is too high, and that leads to an underreach. And also the other way around. If we measure an impedance which is too low, this leads to an overreach. That's sometimes a bit confusing, but you must be careful with these things. Yeah, and we can shift it even more to the right. Nothing significant happens. So you see here, if the fault is at 99%, we measure 132. So depending on our grading, we might even be outside zone 1B we use for teleprotection or whatever. So that is a thing which has to be taken into account. If we move the thing to the other side, of course we have here in this case the opposite situation. You see here we have the fault at now 3% from the left side is 97% from the right side. And we measure 63. That means in this case we measure an impedance which is too low. And in this case the right relay would still react on the fault, although it is at 97%. That means in this case we have an overreach. But this overreach is not a critical thing because it comes from this special situation. Because if we really move close to the bus bar, so theoretically it's a wrong trip if our right relay trips on this fault, but the fault is still on the line. So theoretically is a wrong trip, but practically it trips for a fault on the line. And if we come close to the bus bar, then we have no longer any current flowing here, and then this relay will not do anything. So there is no risk that in this situation the right relay trips on a bus bar fault. So that was the situation with a missing infeed on the right side. That is the situation where we have the strongest effects. Now we can also do the same thing with a little bit a more standard situation. That means I increase the infeed again on the right side. Maybe I bring it to 3,600. No, it doesn't want to be there. Yes. So you see, if we are on the middle of the line, we have, in this case, roughly 2% measurement error. But also there, if we now move the fault to the right, you see here it becomes yellow at 79%. That means a fault at 79% from the left side, in this case, is already seen outside. That means we have a significant underreach, 79% instead of the expected 80%. And in this standard situation, the other side reacts pretty similar. So you see here, it becomes yellow at 18%. 18% from the left side means we have 82% from the right side. That means a fault at 82 is already seen outside. That means also here we have a certain underreach. It's not as big as in the other case, but it is there. And of course, as protection engineers, we always must make up our mind, is that a thing we have to take into account or not? I will discuss that later on. So I will just now like to repeat what we saw in the simulation. So one finding was, if in a parallel line system the two currents have the same direction, then the influence of this parallel line effect leads to a positive measurement error, and that leads to an underreach. If both currents have different direction, we get a negative measurement error, and that may lead to an overreach if we are, in both cases, if we are near the zone limit. And these were the simulated cases. First of all, we had a look at the case where the right side was out of operation. That means in-feed only from the left. In this case, we get the strongest effects, although it is not the typical situation. We made a fault at 72%, and we saw the relay would measure 86%. Setting was 85%. And that means a fault at 72% was seen by the relay, by the bottom left relay, already outside the zone. That means we get an underreach because these two currents have the same direction. We are talking about the measurement of the relay from the left bottom side, which should measure 72%, but it measures 86%. In this case, the weak in-feed side is a little bit a special situation. There we get an overreach, because there the two currents have different directions, as you can see here. But in this case, it's not a critical thing, because if we approach the bus bar, the current will be nearly zero and the right relay will no longer react. Then we had a look at a situation where we had influence in-feed from both sides, in this case not identical, so the right side was a little bit weaker than the left side. Also there we had the same effect. That means for a fault at 79% from the left side, the relay measured a bit more than 85. That means this fault was already seen outside the first zone. That means an underreach, 79 instead of 85. And in this standard case, the same thing happens from the right side. Here a fault at 82% is already seen outside. That means also here we have an underreach. That means as a result, what you can keep in mind, if we talk of influence by parallel lines, we normally have the problem that the relay underreaches in case of earth faults. That is a thing you always have to keep in mind. If we have three-phase faults or two-phase faults, the only thing, the topic is not relevant. So we could stop there, but there is another effect. And you may have cases where the parallel line has to get some maintenance. That means if you take the parallel line out of service, and if you take it out of service, you will normally not open only the breaker on both sides, That would be nice because then you interrupt every current flow. But what you normally do is you ground the line on both sides. And if you have that, you still have parallel lines where you can have current flow. And it's worth to have a look at this situation as well. And we will again do that in my simulation. So you see here the situation we have analyzed already several times. Fault in the middle of the line, parallel line in operation. And now I can disconnect and ground the parallel line. And here again we have a symmetrical situation. Nothing happens. We have a fault current now flowing here, 2.6 kiloamps, also fault current flowing there. And of course, this fault current here will also induce a voltage into this grounded parallel system. But here we have the situation, this current on the left side will induce some voltage there, and the right side will also induce some voltage there. And these two voltages are equal but have different signs, so they compensate each other. So the result is that we have no current flow in the parallel line. But if we now move the current, you see what happens? We have suddenly a current flow in the parallel line, and again by that we get an influence to our measurement. And you see it's not a very critical thing in the first glance. You see here 16.6%. It will still trip, but you see here from the other side, the influence is getting higher, and it looks like overreach or underreach. It's now critical. The impedance we measure is too low. That means we have a risk of overreach. And we can shift the fault a little bit more. Now we are at 15% from the left side. That means 85% from the right side. That means we should be at the zone limit. But the measurement from the right side is still 78. So it sees the fault clearly in the zone. That means even if we move it further, that means in this case, even if the fault is at 0, that means the fault is on the bus bar or even on the beginning of the next line to the left, we still measure something which is in the first zone, less than 85%, according to my setting. That means here in this case, where the parallel line is out of operation and grounded, we have the opposite effect. With the parallel line in operation, we had to deal with underreach, and here in this case, we have to deal with overreach. And of course the same applies for the other side. Also here, if the fault is on the bus bar, or it could even be on the beginning of this line, we still measure from the left side something inside the first zone. And that is now a thing which causes some trouble. If the parallel line is in operation, there is a tendency to get underreach. And if the parallel line is out of operation and grounded, there is a tendency to get overreach. Yeah, for this case also a short summary. So we considered this case. The parallel line is out of service and grounded, and the effect we are dealing with is if we have the fault on our protected line, we have earth current flowing on the protected line, and this earth current influences voltage into the grounded system, and that influences again the measurement. That leads to a current on the parallel line, which is grounded, and this current then influences our measurement. And these screenshots again show what we saw. If we have a fault on the middle of the line, symmetrical conditions, nothing happens. Then we still have induced voltage, so the currents on the faulty line induce voltage in the grounded system. But as that is symmetrical, these two induced voltages have the same size, different signs, so they compensate each other. But if we have a non-symmetrical situation, we had a look at this case, the fault is close to the left side or really on the left side or even on the left bus bar, then the right relay gets a measurement error, which is negative. That means it measures an impedance which is too low, and that leads to an overreach. In this case, with a setting of 85%, we would even see a fault on the left bus bar inside zone 1. And that is a reason why a setting of 85% on parallel lines can be critical. We will come to this issue later on. So that gives a summary of the things we found. In this situation, parallel line, out of service and grounded, both relays will underestimate the reactance at the zone limit, both relays will overreach, and that gives us a risk of a trip on a busbar fault or even on an external fault. So we saw effects going in two different directions. That means in the second part we have now to make up our mind, what can we as protection engineers do with this effect? How do we have to adjust our setting or to add something to avoid problems with this underreach or overreach? And there are three different ways of dealing with the topics. One thing is we can use teleprotection, which is a standard case in transmission systems, or also look at the grading factors. The second thing is we can use the parallel line compensation function, which is available in the relays. And the third possibility is you can adjust zero sequence compensation factors, which is also sometimes done. With that you can compensate a few things, and I will now go through these three possibilities one after the other. So first thing is use of teleprotection modifying grading factors. I wrote here on the right side again the finding: if parallel line is in operation, we have an underreach issue. If the parallel line is grounded, we have an overreach issue. So if we want to do something, we must first of all make our mind, do we want to avoid overreach or underreach? And the first idea could be, yeah, let's first of all talk about underreach, but that's because that's the normal situation. Underreach is no new problem for distance protection, because the first zone in distance protection is always an underreaching zone. Because of all the other measurement errors we have, we normally set it to 80 or 85%. You saw 85% can cause problems. That means we set it to 80%, and from this parallel line effects we get some additional underreach. That means in reality the reach, if we set it to 80, is no longer 80, it is reduced. That means it is no new problem we get. The existing problem that the zone 1 is underreaching is increased a bit, And if you compensate that by teleprotection, teleprotection is the method to compensate this underreaching issue of the first zone. If you have teleprotection activated, you can indeed compensate that. However, you must do calculations to see if the underreach is too high, also if other measurement errors come in, you even may get problems with some teleprotection methods. So that is a thing which has to be analyzed. Increasing the grading factor to compensate the underreach, however, is not a good idea. Why? Because the parallel line is not always in operation. And also, if you increase the grading from maybe 85 to 90 to compensate this underreach, you must always have in mind for double-phase faults and three-phase faults, this underreach doesn't show up, and if you increase the grading factor, you increase the grading factor for these faults and they don't have an underreach. So increasing the grading factor is not a good thing. So one possibility is to avoid or to compensate this additional underreach by teleprotection. That is the underreach story. But we also have overreach if the parallel line is in operation and grounded. And the overreach is a thing which is not compensated by teleprotection. Overreach can lead to wrong trips. And if we have teleprotection or not, wrong trips are there. They will not prevent it by teleprotection. So one issue could be to reduce the grading factor. So instead of using 85% in my example, 80% would be a solution, and that is done in many cases. And if that is not sufficient, there is a possibility to use a separate parameter set in the case where the parallel line is out of service and grounded. Because you normally know that you have the situation, that means then you define a separate parameter set with a reduced grading factors, and you activate that parameter set for the relay in case where the parallel line is out of operation and grounded. What you also should have in mind is that if you use the single-ended fault locator to find out where your fault is, that is based on the same equations. It calculates a bit different, but it's based on the same equations. That means it also suffers from this parallel line influence. That means you get the same measurement errors also into the single-ended fault locator. And if you apply teleprotection or change your grading, the errors in the single-ended fault locator will remain the same. So if you apply this method, maybe using a separate parameter set and using teleprotection, in case of parallel lines, you have to live with these errors in the single-ended fault locator. That brings us to option 2, use of the parallel line compensation. What is that? Remember, in the first part I showed you can set up the equation for the measured phase to ground loop, even taking into account this parallel line coupling. And it's not rocket science, so it's easy to include this into the model for the distance line, for the distance calculation. So it's not an algorithm thing. So the algorithm to do that is available in all relays. The problem is, to do that, you have to know the earth current of the parallel line, because the amount of induced voltage depends on the coupling factors. You have to set them as parameters, and depends on the earth current of the parallel line. And of course, that has to be measured. That means you have to add additional measuring inputs to the relays. And again, that is not a question of relays. The relays have these inputs available or can make them available. The problem is here, you have to do cross-wiring. That means if we look at the bottom left relay, which protects the bottom line, it has, in addition to its own phase currents and earth currents, it has to measure also the earth current of the parallel line. That means you must do some wiring into another bay. And that is additional effort. Okay, you can say you only do it with commissioning and that's done. But my feedback from people is I don't think that very many people apply that. It's theoretically it's the best solution to overcome all these problems I discussed, but you need these cross-wiring, and that means if, for instance, you have to you take one bay out of operation for maintenance, you always must have in mind there is one active current transformer for the parallel way. That means the bays are no longer separated because of this cross-wiring. And my experience is that that is the main point why not a big amount of people really apply this parallel line compensation. That means the idea is all relays measure additionally the residual current on the parallel line. The extended algorithm, that is a thing which is available in all relays. And this solution is correct in all cases. That means even if the parallel line is disconnected and grounded, we can measure this current and we can take it into account and we compensate the effect. And also the single-ended fault locator would be able to work properly. There's only that says there's this disadvantage is this cross-wiring is a bit more complex system, and you may need an additional current input. There's also a way to get around that. You can also live with 4 current inputs by measuring the 3 phase currents of the protected line, and you have 4 current inputs anyhow, and then you can say, okay, you take the 4th current input to measure the current on the parallel line, and the earth current of your own line can be calculated from the 3 phase currents. There's one issue you have to keep in mind if you apply this system. The equations are set up for this situation I show in this picture. So we are talking about the bottom left relay. We measure the distance from the relay to the fault. That means the piece of line we measure is indicated here in yellow. And we also measure the current in the parallel line. That means we can take into account the influence between which the current on the parallel line has on our own measurement. That is the model which is implemented in the relay, and that is exactly valid in this case. The problem, however, is when you do the measurement, you do not know, is the fault on your line or is the fault on the parallel line? That means also the relay in the healthy line does a measurement, and it does not know is the fault on the line or not. And if this relay on the healthy line now also applies the same compensation, it is no longer valid, because you now have a different situation. this yellow part in the bottom diagram, that indicates the measured path for the upper relay. That means it measures along the healthy line and then down to the fault on the parallel line. And for this loop, it assumes that it sees the fault on its own line, which is the upper line, and it assumes the fault it measures on the parallel line, which is in this case the lower line, that these two currents are in parallel for the whole measured distance, which is however not valid, because in the right path you have a complete different situation. You suddenly have two currents which have different direction. That means you are getting an overreach by that anyhow, and then if you add some additional overreach by this compensation, you may end up in an operation of the relay on the healthy line, and that requires an additional add-on to this parallel line compensation function. An add-on which disables the parallel line compensation. And this add-on is normally a pretty easy thing. That means we look at the current on the parallel line and the current on our protected line, and we calculate the ratio. And normally the earth current on the faulty line is higher than the earth current on the healthy line, even in these situations where both currents both see short circuit currents. And this so-called ground current balance function that disables this parallel line compensation function in case the earth current on the own line is lower than the earth current on the parallel line. And by this add-on, by this ground current balance, you avoid that you apply the parallel line compensation in the lower case there where the model is not valid for that part of the system you are measuring at the moment. So that was use of the parallel line compensation. As I said, theoretically the best solution. Practically, many people avoid to use it because it requires this cross-wiring between different bays. And the last thing also people sometimes do is adjusting compensation factors. In the beginning I said one option would be to tune the grading factors. That means to decrease or increase it from 80 or 85%. The problem there is that also affects double phase faults and three phase faults, where we don't have underreach or overreach from parallel line. Another option to influence the reach only for ground phase faults is to tune this earth or residual compensation factor, Kx. You remember that is a thing which has to be calculated from the zero sequence and positive sequence impedances of the system. And what you can, normally you have to calculate it from these impedances, and you have to set the right values. If you set a wrong value there, it will influence the reach in case of ground faults, of earth faults. And that means if you want to avoid an overreach, one possibility is to tune this residual compensation factor in a way that the reach decreases. And that is a possibility people sometimes do. You can then calculate. That means you really you make a wrong setting to reduce, for instance, the overreach. And that is an application which is done. The advantage is this modification will not influence any reach settings for face-to-face faults or three-phase faults. The disadvantage, of course, is we are talking here about underreach if the parallel line is in operation, and overreach if the parallel line is grounded. That means if we want to tune these factors, we must make up our mind, do we want to tune it in direction of underreach or overreach? And a strategy which is often done is that we cover the underreach issues by one factor or by the teleprotection and activate again a different parameter set or a different zone, a special zone, which is only activated if the parallel line is grounded. And this special zone has a modified residual compensation factor. That means you set up one additional zone, or either you can do a complete parameter set, or you can say you set up a special zone 1 dash or whatever, with a modified, a wrong residual compensation factor, and that is modified in a way that if the parallel line is grounded, disconnected and grounded, it will reduce the overreach to an acceptable value, and you activate this zone only if you have this state, which is not very often. That is only if the parallel line undergoes some maintenance. So that is also an option where you don't need an additional wiring, but you see it's also a thing which requires some calculations so that you can apply it properly. With that we come to the end. So we saw parallel lines may influence the distance measurement only for face-to-ground faults, and we also had a look at different options to compensate the effects resulting from that to avoid any maloperation of our distance protection. Thank you for listening.
Dear audience, if you are interested in more detailed information and practical training, please visit our training platform at Siemens Power Academy. I am confident you find the right resources and training there. A link to the recording and the slides will be sent to all participants. Thank you for your active participation. I look forward to meet you soon. Stay safe and take care. Goodbye.
실제로 트럼프 대통령은 텍사스로 오는 기내에서 전진 지시를 내린 상태였습니다. 여기는 붙어네. 다시? 저거 여기다 붙이는 거. 뭐 붙이는 게 있어? 남자도 여기 붙이는 게 있어. 그래도 이거. 촬영 이거. 한보다 내가